one next door, and Mr. Strauss is still there.
I'll be back in just a minute.
Okay. And I said to go ahead and try to do the snowman worksheet and see how you did. So what we're going to do first is we're going to go over the snowman worksheet, make sure everybody understands and everybody was getting the right answers on that. So, probability from pictures. This is what you actually hope I ask you on the test, is I give you a picture and ask you to calculate probabilities from it, because this is the easy way. This is the easy stuff to do. All you have to do is actually count. So what we're going to focus on is getting the right notation, learning how to write the correct probability notation, and making sure that you understand that I don't care if you use the symbols that the book uses or not. I don't care about the union symbol and the intersection symbol and the line and all that. I'm going to have you write out words. I think people understand words better than they do symbols. Okay? So we're going to practice writing notation as well as doing the probabilities. So the first one asks us is, what is the probability, given all these snowmen up here, what is the probability that a randomly selected snowman is wearing a scarf? So that key word, that important word, was the snowman was wearing a scarf. And the first thing that I want you to do is I want you to count those snowmen and tell me how many there are total. Maybe that's better. How many snowmen are in that picture? 18. Okay. That's going to be throughout this whole entire thing. There's a total of 18 snowmen. And it's saying what is the probability that we randomly select a snowman, and that snowman is wearing a scarf. So rather than using letters for everything, I just go ahead and write out the word. Probability that the snowman's wearing a scarf, P of scarf. And in order to find that out, the first thing that I'm going to do is I'm going to count all the snowmen that have scarves. Here's 1, 2, 3, 4, 5, 6, 7, 8. So 8 of those snowmen were wearing scarves. That means that the probability is 8 who were wearing scarves out of 18 total snowmen. Now, I am not my math lab. I am not my stat lab. I want to see that. I want to see what you counted. You can simplify the fraction if you want to. Your calculator simplifies fractions just fine. If you want your calculator to simplify that and say it's 4/9, that's fine. 4/9 is the correct answer. But I want to see that this is what you had first. If you change it to a decimal or a percentage, I want to see this is what you had first. Because this tells me you knew how to do it. Okay? Seeing that actual original fraction tells me you knew how to do it. And that's the important thing to me. I want to know you know how to do it. Not that the mistake was you rounded wrong, or you converted the fraction wrong or something like that. Now, if it is MyMathLab that you're answering these kinds of things for, in order to change that to a reduced fraction, you enter in your fraction, and you always, unless you have a TI-84 that makes fractions, you always enter your fractions in parentheses so that you just get in the habit of doing it, because most of the time you'll need to. And then in order to change it to a reduced fraction, you press the math button and the enter button to change it into a fraction, and it'll change it to a reduced fraction. So this is an acceptable answer. And this is an acceptable answer. And if I tell you to round that to 3 decimal places, that's an acceptable answer. And if I tell you to change it to a percentage, I always want you to have at least 1 percentage decimal point. So I want you to round to 3 decimals before you round to a percent, not just 2. Don't call that 44%, because it's actually a little bit more. I'm sorry, it's not 44.1 either. It's 44.4%. So don't call that 44%. It's 44.4%. Okay? Now, all of those are correct. Every one of those is correct. But remember, what I want to see, regardless of whatever the rest of this is, I want to see this. Because that's what tells me you knew how to do the problem. Okay? Any questions? Okay, same situation, and notice here, every one of these I made a clean picture because it's easier to see what we're counting. This one says, what is the probability that a randomly selected snowman, and we already know there's 18 snowmen, right? Is wearing a hat. What's the probability the snowman is wearing a hat? Okay. 1, 2, 3, 4, 5, 6, 7 snowmen, and each of those 7 snowmen are wearing a hat. So it's 7 over 18. That's what I want to see. I want to see that answer. Now, if you want to change that to a decimal or a percent, that's fine. You practice that. 7 divided by 18, and that is an already reduced fraction, but if you ask your calculator 7 divided by 18, change this to a fraction, it's going to come back and say 7 divided by 18. But it will change it to a decimal for you. If you're going to change it to a decimal, round it to no less than 3 decimal places, ever. Never less than 3. Sometimes I'll tell you to round it to 4. And if you're going to change it to a percentage, round it to 3 decimals, and then change it to a percent.
So, on this question, number 3, it says, snowman is wearing a hat or a scarf.
Okay, that's the next one.
Oh.
Okay, and yeah, we're going to do that one. So is everybody clear on how I want you to answer your probabilities? This first 2, these are not hard to do. All we got to do is count. We know there's 18 snowmen, so it's not really tough to count all of these. The notation's what I've been focusing on up to this point. How do you write it, and when do you quit? What part do I want to see? I want to see that first answer. So this one is the one you're talking about. This one says what is the probability that a randomly selected snowman, that's going to be P of something, is wearing a hat or a scarf? And that word in there that's very important to you at this moment is the fact that it's or. The snowman doesn't have to be wearing both. The snowman only has to be wearing one or the other. Okay? So here's what I'm going to do. I'm first going to mark all the snowmen that are wearing hats. I believe that's all the ones that are wearing hats. Do you agree? Then I'm going to go back and I'm going to mark all the ones that are wearing scarves, because it's a hat or a scarf. And none of the ones that I have left have scarves on. And now here's what I want to count. This is the important part. I don't want to count all of the hats and then go back and count all of the scarves. Why not? Some of them are wearing both. So if I count this one because he's wearing a hat, and if I count this one because he's wearing a hat, and I count this one because he's wearing a hat, and then come back around and count those same three snowmen because they're wearing a scarf, that's not going to be the number of snowmen that are wearing either a hat or a scarf. Okay? Now, you need a rule to do that unless you've got pictures. If you've got pictures, then you go and mark the ones that you need to count. And then you only count the ones you marked. So this is snowman number 1. This is snowman number 2. This is snowman number 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 snowmen that I counted out of the total of 18 snowmen that were wearing either a hat or a scarf. Okay? I was very careful not to double count the ones that were wearing that had both, because they only got to be counted one way or the other. Okay? Now, to review a little vocabulary from last time, that's because wearing a hat and wearing a scarf for those snowmen is not mutually exclusive. It is not disjoint, because you have snowmen that both wear hats and wear scarves. Okay? So those are not disjoint events. If it were, then the snowman could either have a hat or the snowman could have a scarf, but not both. Okay? Now the next question is going to sound a little similar to that. This one says, what's the probability if you randomly select a snowman that that snowman is wearing a hat and a scarf? A hat and a scarf. Do I count this snowman? Nope. Because he's only wearing a scarf. He doesn't have a hat. Do I count that snowman? No, because he's wearing a hat. He doesn't have a scarf. This says both. That's the key to remember. The word and means both. The word or means either or. Either one or the other, but not both. And means both. So the only snowmen I'm going to count here are going to be the ones that are wearing hats and scarves. He's got a hat and a scarf. This one's got a hat and a scarf. This one's got a hat and a scarf. Do any of the others have hats and scarves? No. So that probability is P, hat and scarf. There are 3 snowmen like that out of 18. And that's 1/6 or 0.166666 or 16.7% or 0.167. All those other things are just arithmetic that the calculator can do. I want to know that you can do this. Okay? Now, when I give you the answers to the worksheet for Chapter 4, I'm going to give you those answers as percentages. It's going to be up to you to change your raw fraction and make sure your percentage matches mine. But you will have something to aim at. You'll know if you got it right or not. And then if your fraction doesn't match my percentage, that's when you need to ask a question right there in the folder and say, Ms. Flint, why is number 3 this? I got this. So that way I can help you if you had, because if this is where you made the mistake, that's what we need to fix. Okay? What's the probability that a randomly selected snowman is wearing a scarf? Okay, so far so good. We know how to do that one. Then there's a little catch. Given that they have buttons, am I counting all 18 snowmen now? No. Which snowmen do I count? Only the ones that have buttons. Okay, this one's got buttons. This one's got buttons. This one's got a bunch of buttons. This one doesn't have any buttons. No buttons. He's got some buttons. There's some buttons. There's some buttons. There's some buttons. This one's got buttons. This one's got buttons. That one's got buttons. No buttons. This one's got buttons. This one's got a bunch. This one's got a bunch. This one's got a bunch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Did I count right? Okay, so there are 14 snowmen with buttons. And that's going to be important because that's the only snowman I'm going to count from. I am not the least bit interested in Frosty. Because Frosty didn't have any buttons. Okay? So I'm not counting that one. I'm only counting the 14 that had buttons. So that means when I write the probability that they're wearing a scarf. Now, the notation in the book looks like this. That line is read, given that. okay? If you don't want to write that line, and it's okay with me if you don't, you can write probability scarf given buttons. I like words fine. I understand words. So now I need to count for all those snowmen that have buttons, which one of them have a scarf. Well, this one does. So there's 1, 2, 3, 4, 5, 6, 7, 8. Have 8 snowmen that have scarves. Out of 14 snowmen that had buttons. When the word given is in your probability, that means that the number on the bottom of your probability fraction is going to change. And that you're only counting the ones that it says given. So as long as you show me this, then you can tell me it's 4/7 or whatever decimal or percentage that changes to. But show me that first step. I want to be able to count you right when you do it right. Okay? Any questions so far? As long as we're doing things like this, is probability as hard as you thought it was going to be?
As long as I have pictures.
Yeah, so that's me. As long as I have pictures, or if I don't have a picture, if I can draw one. If you'll just let me draw a picture, I can figure it out. Because I'm one of those people that needs to see the pictures. In fact, I've got a little quiz that I'm going to give you on Monday, and I'm going to encourage you to draw the pictures. Now, a few more questions. Same bunch of snowmen still. What is the probability, and here's the monkey wrench, what is the probability that 3 randomly selected snowmen are wearing hats? And assume that this is without replacement. Without replacement. So what that means is that when I reach in and pick the snowman, number 1, the snowman I pick has to be wearing a hat every time. And on the second trial, when I reach in to pick snowman number 2, snowman number 1 isn't sitting on the table anymore. Snowman number 2 is over here in a box. Okay? And then when I reach in to get snowman number 3 that's wearing the hat, snowman 1 and 2 with hats are over here in the box. So there's 2 things going to change every time that I do a new probability for the next snowman. I'm going to have 1 fewer snowman that has a hat, because that one's not over there to pick from anymore. And I'm going to have 1 fewer snowman on the sheet. Okay? So we know there's 18 snowmen. Not only that, but I think we already counted the hats and said that there were 7 that have hats. So the probability of the first snowman wearing a hat would be 7 out of 18. Okay? Now, I'm not putting that snowman back in. How many snowmen are left? 17. How many of those 17 snowmen have hats? Only 6. Now I'm going to reach in one more time. How many snowmen left to pick from? How many of them have hats? So I have found the probability the first one has a hat, and I found the probability the second one has a hat, and I found the probability the third one has a hat. Taking into account that I didn't put any of them back after I picked them. And this is the place where the words or and have to come back and haunt you, because you've got to remember that in order for me to have 3 snowmen that have hats, what I actually have to get is I have to get hat number 1, hat on snowman number 2, and a hat on snowman number 3. That word "and" is a very important word, because the word "and" tells you what arithmetic operation you need to do to get the probability. You need to multiply. If I had said "or," you could add. But because I said "and," you have to multiply to figure this one out. Now, I want to see that step. Regardless of what happens after that, I want to see that, because that tells me you knew how to do it. This is one, though, where actually multiplying it out is kind of annoying, and I don't want to have to go through putting the problem in 2 or 3 times, so I'm going to go ahead and get the reduced fraction for the answer. But when I post the answers, this is what you're going to see. It'd be nice if I could type it right. .04289 because if I want you to round it, say for example, to 4 decimal places, then I would want you to look at that 9 and say, okay, that 8 becomes 9. Or if I told you to round it to 3 decimal places, and I may round my answer to 3 decimal places, then I would look at the 8 and say that 2 needs to become 3. So I might give you one of those 2 answers, but if you got the fractions that you multiplied correctly, you're going to get that answer. You're just going to get a lot more decimals. And then sometimes what I post is I just post the whole entire thing the calculator told me and let you compare, because it's easier for you. Okay? But all of those are good answers as long as I see that step. and you want to change the percentages, you could do that too. Anybody have any questions? Okay, we're almost done with this one. What's the probability that a randomly selected snowman, oh good, we're back to 1, is wearing a hat given that he's wearing a scarf? First, I have to go and count all the ones that are wearing scarves, regardless of whether they're wearing hats. 1, 2, 3, 4, 5, 6, 7, 8 snowmen that have scarves. None of the others do. Now I go back and count the ones that are wearing hats. But I only count out of the ones that have a scarf. 1, 2, 3, and I don't see any of the others that are wearing scarves wearing hats. Do you? So 3 of those had a hat. So that means my probability then of hat given scarf is the 3 that have hats out of the 8 that wore scarves. Okay? Just don't get this confused with the ones that are wearing hats and scarves. Okay? If I just say, what's the probability you randomly select a snowman that's wearing a hat and a scarf, yeah, that is still those same 3 snowmen, but then I'm selecting them out of the whole entire group of 18 snowmen. If I don't specify that I was only looking at the ones that were wearing scarves. That's where you have to be careful, is when you see that word given. That becomes a very important word because that changes your denominator. Okay? This one sounds the same, but it's not. What's the probability a randomly selected snowman is wearing a scarf given that he's wearing a hat? We're only counting the ones that have hats. We have 7 that have hats. And of those 7 with hats, that same 3 also were wearing a scarf. So we're still talking about that same 3 snowmen. That were wearing a hat and a scarf, but we're only talking about the ones that were wearing hats to begin with. I want you to be sure and compare that answer to this one. And notice how that's different. The word that comes after given tells you what the bottom of the fraction is. In both cases, we were talking about the same three snowmen, the ones that had a hat and scarf both, but we were only counting in the first one out of the ones that had scarves, and in the second one, we were only counting out of the ones that had hats. So just be careful of the wording. If there's anything that will trip you up, is if you're not a careful reader. You need to be a very careful reader in probability. Okay? So that's the last of our snowmen problems, and you've got one to work on that's similar to this. And now we're going to talk about something called contingency tables. Contingency tables. I want you to know that in this class, for everything that I do, I will give you the totals, the column and the row totals in a contingency table, because I don't want you to mess up because you added wrong going across the row or going down the column. So I'm always going to total up the columns and the rows for you. This is what a contingency table looks like. And I'm going to start out by talking to you about some things that you know from reading the table. First of all, this is a survey taken at a local elementary school. They surveyed kids from all of the grades, K through 5. They surveyed a total of 29 kindergartners and 35 first graders and 31 second graders and 38 each of the third and the fourth grade. And then they surveyed 41 fifth graders. So of everybody in the school, they surveyed a total of 212 kids. What they asked them about was which one of these PE activities that they preferred to do. So we know that of that 212, 46 of those kids preferred tug of war. 45 of them preferred dodgeball. 50 of them preferred jumping rope. And 71 of them preferred freeze tag. You would not want to have to count pictures on this one because you'd have a picture of 212 different kids. And each one of those kids would have to have 2 different labels, and that would get old really fast. So this table is a much easier way to calculate probabilities if you need to, because it's organized. The only thing you have to do is be sure that you understand what every single number in this table actually means. And I'm going to go through some examples with you first, before we ever do probabilities. Tell me about those 15 kids. What do you know about them? Okay, you know they're in the 4th grade. What else do you know? And like jumping rope. The reason you know that is because they're in the row that says they're in the 4th grade. But they're in the column that says they like to jump rope. So that we would describe these kids as 4th graders that like to jump rope. How many kids are there in the 2nd grade that prefer dodgeball? 4. Because I said they were kids in the 2nd grade and that they preferred dodgeball. So I'm looking for those 4 kids right there. Okay? Now they're still 2nd graders, but they also like dodgeball. This is called a two-way table or a contingency table. A lot of textbooks call it a two-way table because it has rows and it has columns that sorts out your data, your survey respondents, according to two different categories. And it makes it easier to figure out where everybody is. So from there, we can actually answer probability questions. We just have to be careful to understand the questions that we're answering. So we're going to start with a clean table every time we do this. What's the probability? That means we're going to write a P statement. That a student selected at random prefers dodgeball. How many kids prefer dodgeball? How many kids are there in the whole survey? And there again, you can reduce the fraction, you can make a decimal, you can make a percentage point rounded to 3 decimals before you make the percent. Okay, I'm focusing on how to do the probability, not the arithmetic. Does this make sense to everybody? What's the probability that a student selected at random is in the first grade? How many first graders? Okay. 35 first graders. And since we're selecting at random, that's out of the whole group. There weren't any other conditions in there. So the probability of selecting a first grader was 35 out of 312, or excuse me, 212. Okay? What's the probability that a student selected at random prefers tug of war or jumping rope? Are tug of war and jumping rope mutually exclusive? Given the context of the survey, yes, I know there are people that can play tug of war that also jump rope, but they asked these kids, which one do you prefer? You don't get to prefer both of them. So is this disjoint? Can one kid have answered both answers? No, because they had to pick one. Okay? So this is disjoint. And because it's disjoint, all we really need to do is add the number of kids together that prefer jumping rope and the ones that were preferring tug of war. So 46 plus 50 is 96 out of the 212. So the probability that they preferred tug of war or jumping rope was 96 kids out of 212 kids total. Okay? Now, these are going to get a little harder as we go along, so pay careful attention. If you don't understand something, ask. We've seen this one before. What is the probability that a student selected at random prefers tug of war, given that they are in the 3rd grade? What is the only row in that table that I am interested in? The 3rd graders. I really don't care anything about the 1st graders. I don't care anything about the 5th graders at this point. I'm only looking at 3rd graders. And there are a total of 38 3rd graders. That means the denominator of my probability is going to be 38. Now I can read the rest of the question. What's the problem? What's the probability, if they're in the 3rd grade, they prefer tug of war? How many of those 38 kids preferred tug of war? 13. See some puzzled looks. Did I have a question?
No.
Okay. That's why I'm waiting, because sometimes you'll look at it for long and go, oh, I see.
Yeah.
And then sometimes I need to say something, but I don't want to interfere with your figuring it out for yourself. Okay? Okay, this sounds like the same question, but it's not quite. What's the probability a student is in the 3rd grade, given that they prefer tug of war? Where's the only kids that I'm interested in? In the tug of war column. The rest of that table might as well not even exist when I'm trying to answer this question. And that's 46 kids. Now all I have to do is look at just those 46 kids and find the ones that are in the 3rd grade. And there's 13 of them. So there's my probability. 13 out of 46. Okay? Different situation. There's that word and. besides making you always think of multiplication if you're trying to select more than one, or in other words, you're doing a compound event where you're going to pick more than one time, that word and always should make you a little more cautious than the word or. But and sometimes is what causes you problems with or. What does it mean for a student to be in the 4th grade and prefer freeze tag? How many kids are there like that? Where are they? Okay, they're just in the column that talks about freeze tag. Because it says they prefer freeze tag. But they're only in the row of the 4th graders. And the place that those overlapped was 7. Now my question that I'm going to ask you here doesn't have anything to do with the probability, but it has to do with making sure you're understanding those earlier words from last time. Is preferring freeze tag and being in the 4th grade disjoint? Is being a 4th grader disjoint from preferring to play freeze tag? Why or why not? You have kids that are in the 4th grade that prefer freeze tag. Therefore, they can both occur on one individual student, okay? This is where you find the ones that are not disjoint. Anything that's in any part of this table, any of these numbers in here represent individuals that are in 2 different categories, and those 2 categories are not disjoint, okay, because they're overlapping. That's a key thing to realize. Now, since that's the only thing that they ask us about was, where's the ones that are in those 2 categories, we're talking about out of the whole entire school. So the probability in this case is 7 over 212. And I'm bringing that up because, I've told you, I've mentioned to you the shortcut, and I know you've got it stuck up here. And means multiply. And means multiply. You don't need to multiply to answer the question. You only use a rule if you can't answer the question any other way. You can answer this question without multiplying anything. You don't need to. Okay? Don't try to do arithmetic when you don't have to. However, remember that was there. Because the next question is very much like it. Or, what is the probability that we select a student at random out of all 212 that either is in the 4th grade or prefers freeze tag? Okay, here's my 4th graders. That's all my 4th graders. There's all the kids. that prefer freeze tag. How many total are in one column or the other? One group or the other? I have somebody that says there's 109. Anybody have a different idea to offer? You said 105? Anybody else? I'm not saying anybody's right or wrong right now. How many? Anybody have another idea? What's 71 plus 38? Ah. So then the question is, why is this the right answer? That's right. You counted these kids when they were fourth graders. You can't come back and count them again as part of that 71 that preferred freeze tag. They don't get to count twice. Okay? So it is 71 plus 38 minus 7. And 109 minus 7 is 102. I suspect that the 105 was somebody trying to do something similar to that, but tried to do it in their head. Okay? So the correct answer is 102 out of 212. Because you had to take into account that you were double counting those 7 kids. So what you do here is you're going to take the total number of fourth graders plus the total number of kids that preferred freeze tag, but you're going to subtract back out the ones that you already counted because they were fourth graders. Because they don't count twice. Now you can show me all that work, but I have to see this. You write down as much of that as you need to remember how to do it. But I have to see that answer because that's the right answer. Okay? It probably will help you to actually show me this step. Because that way, if you wrote down that step, but you did it in your head, which I do it all the time, and say 2 plus 7 is 14 because my brain just went haywire. And if I mess that up, but if I've written down the correct step, I'm not going to count it wrong here if you had it right there. Okay? I understand people make mistakes doing math in their head. Okay, anybody have any questions on this one? Okay, that's actually the last one of those. So here's what we're going to do. I'm actually going to stop the recording here. There is? Okay, let me flip through and see if maybe I missed one. I may have picked up 2 sheets. Okay, I do not have two others, but we will. I'll let you tell me what the questions are. Because I do have a clean copy. Wait, maybe it's under this. No, that's somebody else's stuff. I do have one more clean copy and one that's not written on too badly. What's the next question that y'all have?
What is the probability that 2 students selected at random are in kindergarten?
Okay. Okay, probability 2 students selected at random are in kindergarten. Does it say with or without replacement? Okay. If you actually don't replace the student, and that student gets picked again because they could the second time, would you have 2 students? No. So in that case, would you not have to assume that you're not going to replace the first kid? Does that make sense? Okay. So even though it didn't spell out that you weren't going to replace the first kid before you got the second one, you have to. You're not going to get 2 kids. You're going to have to not replace that first kid. So what we're going to do is we're going to find the probability that kid number 1 is in kindergarten and kid number 2 is in kindergarten, given, of course, that kid number 1 was also in kindergarten. Okay? That's probability notation, and I don't care if you write it down that way or not. What matters is how we think through this. How many kindergartners are there? Okay, 29 kindergartners. We don't care what sport they like, so we're not going to pay any attention to the sports. What's the probability I randomly select a kid from this group and select a kindergartner? Okay. Now, I need another kid, so I'm going to randomly select another kid. I've still got kindergartner number 1 over here by the hand. He's not in that 212 anymore, or she. So, what's the probability now that if I draw another kid out of that group, I'm going to get a kindergartner? Okay, 28 over 211 because I've lost a kindergartner and I've lost a student. And that's why I put that part about given kindergartner number 1, because I kept that one out. Okay, that makes that, those are not dependent events anymore. Because the probability I got kindergartner number 2 was influenced by the probability that I got kindergartner number 1. So that wasn't independent. Now I still have this word and. What does and tell me I need to do with this? Okay, I need to multiply those. And it didn't like that at all. It said, no, I'm not doing that as a fraction. So when it does that, you don't have to put the answer as a fraction. The answer is 0.01815. And if I were rounding this to 3 decimal places, that would be 0.019 or 1.9%. Is there another? 815, okay. Scratch that. So if I want my answer rounded so that I'll have three decimals, so I'll have 1 decimal place for my percent. Then I would call that 0.018, or moving the decimal 2 places, it will be 1.8%. Okay? Sometimes you do need the rule, but don't use it till you have to have it. Okay? What was your last question?
What is the probability that a student selected at random is in the 5th grade given that they prefer dodgeball?
Okay, given that they are preferring dodgeball. Here's the dodgeball kids. And there's 45 of them. That's the given, okay? Given that they prefer dodgeball. Which means that when I do my probability, I'm only talking about those 45 kids, not all 212. And what was the probability they're in the 5th grade, did you say?
Yeah.
Okay, probability they're in the 5th grade would be these 14 kids right here. So 14 out of 45. Okay? I'm going to let y'all take about a 10-minute break because people need to get up and stretch and get your brain working again. It's funny how tired your rear end hurting can make your brain be. So get up, and if nothing else, go get a drink of water, walk outside, stretch, take a couple of minutes, and then we're going to come back and I'm going to start chapter 5. I'm not going to finish it. I'm just going to start it. Because there's a chapter 5 assignment that I want you to get done in Shobi before Monday. And it's equivalent to the first thing that we're going to do. And I want to practice with you in class before I have you do it. And I'm going to tell you what it is. And in fact, I'm going to let you take about 15 minutes. And then this is all we're going to do. Of your chapter 5 notes, I want you to take the page that has 9 questions about probability statements. And I want you to take about 15 minutes, take a break, don't just sit here, take a break, and then come back and work with the people next to you and come to an agreement about how to write that probability statement. Okay? And you're going to need inequality signs to do it. I'm going to write the inequality signs you can use on the board. That one you're probably not going to use because that's if there's only one single value. You're talking about here a range of values. This is equal to or less than. This is equal or greater than. This is just simply less than, and this is just greater than or more than. And I want you to write probability X equals, and there's a number in everything in one of those statements. So I want you to write probability parentheses X and then one of those signs. And then the number that you should put. Okay? You have until 2010. Don't spend too much time on it.
So which assignment is for chapter 5?
Okay, this is going to be important in chapter 5 because knowing what signs you use will tell you how to do the problem on your calculator. The calculator will give you the right answer for whatever you ask it. You have to know how to ask it the right question. Okay? Find the probability. We know all of these, when it says find the probability, means P parentheses to get started. Find the probability that the number of roses in a mixed bouquet, which we're going to call X, is at least 8. Now, in every one of these, what you need to think about is the number you're looking at. Is that the top number or is it the bottom number? And if you can't do it any other way, if you have 9, do you have at least 8?
Yeah.
If you have 7, do you have at least 8? No. So it's going that direction. 8 is not the top number. At least means it's at the bottom. Okay? At least also means it includes. It is the same thing as saying 8 or more. Okay? So since it includes 8 and it goes up, if it includes, there's going to be an equals to. And if it's going up, then your arrow is going to point to the right. That means 8 or more. More goes to the right, less goes to the left. Don't confuse the word least and less. Least means the smallest. Less means go away, go down. Okay? Least and less do not mean the same thing. The second one says to find the probability that the number of couples dining in a restaurant is at most 5. Is 5 the top or the bottom?
The bottom.
If you have one diner, do you have at most 5? At most 5. Yes. If you have 6 diners, do you have at most 5? No. 6 is more than 5. 5 is your top number. 6 is more than 5. This is supposed to be the most you can have. And since that's your top number, you can't have 6 and have at most 5. You're going down. Now, a good way to think about that, you have an apartment, it's the holidays, you have family that wants to come and spend the holiday with you, you have your bedroom, you have another bedroom, and you have a fold-away couch. One of your friends has a sleeping bag or you have a sleeping bag. So you're not sleeping anybody in your room. That's your room, okay? You have a guest room. 2 people can sleep in the guest room. 2 people will sleep on the couch. 1 can sleep in the sleeping bag. What do you do if 6 people show up? Go to a hotel. I have at most space to sleep 5 people. Okay? That's what at most is. I have a limit. I can't go any higher than this. Okay? Find the probability that the number of trout caught during the last fishing trip was less than 17. Less than seems like it should be easy. Less than, which way is the arrow going to go? Less than, it's going to go to the left. Because these fish down here are all less than 17. So I'm going left. What about 17? Is 17 included or not? Is 17 less than 17? No. So you do not include 17. you only include 16. So that's x is less than 17, which is exactly the same thing as the probability x is equal to or less than 16. Those both mean the same thing. And you need to understand that they both need to that they both mean the same thing. That's going to be important. Okay? This is the one that everybody has the hardest time with. Put everything you ever learned about between two numbers in the trash can right now. Put it in the trash can, because I'm going to show you a way to do it that you can't mess up. Okay? Where does that say x is in regards to the numbers 10 and 13? It's in between. Here's 10, here's 13, there's x. It's between, okay? Put it between. That's not really where people mess up. Where people mess up is they point the errors the wrong way. Once you put x between those two numbers, you only need to ask yourself one question. Is 10 greater than or is it less than 13? 10's less than 13, right? Those arrows always point to the left because you always start with the little number and go to the big number. And since it's going from the little number to the big number, it's always going to point down to the little number. Okay? The fact that it said inclusive just means that you include an equal sign. That's all there is to it. Just remember that if it's between two numbers, the arrows always go left, never right. 10 is never bigger than 13. Okay? Get it up there where you can see it better. Find the probability the number of cars caught speeding on a local highway is no more than 21. No means not. Think about what your mama told you when you wanted to do something and she said you couldn't. No, you cannot. That was closely followed by because I said so. Okay? No, you cannot. No, not. If it's not more than 21, can it be 22? No, because 22 is more than 21. So it has to go the other way. Is 21 okay? Yeah, because 21 is the same as 21. It's not more than 21, it is 21. Okay? Probability that the number of books on a bookshelf in an office is no, as in not. No, you cannot. Is no less than or not less than 52. Can you have 51 books?
No.
No, because it's not less. You can't have less than 52. 52 is the beginning of something. If it's not less than 52, what is it? It's greater than, it's more than. So that means it's gonna go that direction. You can start at 52 and you can go higher, but you can't go less than 52. Okay? Number of pencils in a pencil caddy is 18 or fewer. Which way does fewer go, up or down? Has to go down. 2 is fewer than 18, 1 is fewer than 18, 17 is fewer than 18. That means it's going to be less than. And it's 18 or fewer, so it could be 18. Okay? Between 20 and 23. 20, 23, put X between them. 20 is less than 23. It says inclusive. Add an equal sign. Okay? One more. At most. Is 41 at the top or the bottom of your list? It's at the top of your list. Can't go any higher. Got to go lower. This means the same as equal to or less than. Okay? Now you've got a worksheet in Shovie. Do that one worksheet. Get it done as soon as you can. The sooner you do it after you look at this, probably the better you'll do on it. And then go ahead and turn it in, and I'll go ahead and look at it. And if it's not right, I'm just going to circle the ones that you got wrong and put a little note in there and say, try again. I'm not going to tell you right answers right away. I'm just going to say, you got these right, you got these wrong. Go look at these again. The only way to get these is practice. Y'all have a great